All right, welcome to Chapter 17 on lipids. So similar to the previous chapter on carbohydrates, lipids are also biomolecules. So yes, they are organic molecules, but in addition to that, they are used in biological systems and organisms. It says here that they contain fatty acids and or a steroid nucleus. In addition to fatty acids, there's a few other compounds that we'll see in just a moment. So, and I'll just say here, and others. What makes lipids different from most other classes of compounds that we'll talk about, even biomolecules like carbohydrates and later on amino acids and proteins, is that lipids are classified not on what functional groups are present, but on a physical property, and that is their solubility. Lipids are essentially defined as biomolecules that are not soluble in water. So the Greek word lipos means fat. They are not soluble in water, but they are soluble. So it says here extracted. So they are soluble in organic solvents. All right, so we'll be talking about a number of these different types of lipids. We'll start off with waxes and then fats and oils. These triacylglycerols are also known as triglycerides, glycerophospholipids, prostaglandins, steroids. And then after steroids, we'll also talk about cell membranes. So maybe a sixth topic here. We'll talk about cell membranes. Just a little bit about cell membranes and what we call the fluid mosaic model. Now on the next slide, which we'll be referring to quite a bit, we will see examples of each of these. Okay, so if there is one slide that you should really pay attention to in this lecture, is this slide here. So all right, we have lipids. Lipids, again, biomolecules that are not water soluble. And we will talk about fatty acids first. One particular type of fatty acid, well, I should say prostaglandins are derived from one particular type of prostaglandin. And then we'll talk about waxes, triacylglycerols, these are or triglycerides, phospholipids, sphingolipids, glycosphingolipids, that would be 5 steroids. Under each one of these there are several different kinds, but we'll start off simply with just fatty acids. This is something you've actually already seen a little bit. Okay, so fatty acids are long chain, typically 12 to 18 carbons, so C12 to C18. Actually it says 18, but that prostaglandins that we actually talked about are C20. So 20 carbons. Again, they're insoluble in water, and they can be saturated or unsaturated. What do we mean by saturated? Well, basically we mean these guys have an alkane chain, and so they have only carbon-carbon single bonds. Unsaturated, these are alkenes. So where we had talked about fatty acids a little bit before was in that chapter on alkenes, saturated and unsaturated. So alkenes, remember, have a carbon-carbon double bond. Here's a fatty acid with a double bond here. Now, remember, these are they're carboxylic acids, so they're organic acids. Here's the acid functional group. So let me just draw another one up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, remember this carboxyl group. Looks like that. Okay, so these are all organic acids. Just really briefly, condensed structural formula. Here we have a condensed structural formula. There's 6 CH2 units in a row, and then CH3 on the end, and then the acid group. So we have a number of CH2 units. I won't make maybe I'll 1, 2, 3, 4 CH3 in the end, that'd be 5, and so this is 6 carbons. This would be methyl, ethyl, propyl, butyl, pentyl, hexyl. So this is hexanoic acid in the IUPAC nomenclature. Here we have 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? So it would be octanoic acid. Typically you'll see it drawn this way though in the skeletal structure. And often it's drawn, the carboxyl group is drawn as COOH. Okay, so again, saturated fatty acids just have carbon-carbon single bonds. Now, something about, we'll talk more about this later. Okay, so stearic acid here, this has 16 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, sorry, 18 carbons. So it's 18 carbons long. So stearic acid has 18 carbons. It is a saturated fat, so only carbon-carbon single bonds. And because it's saturated, these what we call alkyl chains here, they fit together very nicely, and you maximize the interaction between them. When we melt something, we're basically breaking, when we melt something, there are van der Waal interactions between these chains, and I'll just put a bunch of them in here like that. So van der Waal interparticle interactions that hold these together. The longer the chain, the more van der Waal interactions, which means it takes more energy to break those interactions, so it has a higher melting point. Also, if they line up really nicely, so there's strong attraction between them because they line up so nice. They fit together closely in this regular pattern, so it maximizes the van der Waal interaction, and these saturated fats have higher melting points, which tends to make them, so they are typically solids at room temperature. And stearic acid, think steer, like cow or steak or whatever. So steer, this is that the fat on the cow. This is that stearic acid. Looks like a ribeye. Okay, so some examples here of these saturated fats, right? You don't have to know the names of any of these. I'm not going to ask you to know the names of any of these, but there are some things you need to be aware of. Again, notice as the carbons get bigger, 10, 12, 14, 16, the melting points increase. So as the alkyl chain, that is all these CH2 groups here, get longer, as the alkyl chain gets larger, the melting points increase. All right. Another thing to notice here is these are all even numbered. Now, we probably won't have time to talk about this in lecture. We will talk about how fatty acids are metabolized and how they're broken down, but we won't talk about how they're made. And it turns out they're typically made by 2 carbons at a time, right? So if they're put together 2 carbons at a time, naturally you're going to get an even number. So I won't say this is true for all fatty acids, but most are even numbered. Right? And that's because they're put together 2 carbons at a time. Again, don't worry about remembering the names, or certainly not the melting points or where they come from, but notice stearic acid, right, comes from animal fat. Palmitic acid, this is interesting, comes from palm, so this is palm oil. Okay, but at 62 degrees, this is well above room temperature, right? What is room temperature in Celsius? Is about 20 degrees Celsius. So anything that has a melting point above room temperature, anything that has a melting point above 20 degrees Celsius is going to be a solid at room temperature. So these are typically solids. Okay, so we talked about saturated fats and now unsaturated fats, right? Saturated fats have 1 or more double bond. If it's polyunsaturated, now when we talked about carbohydrates, we talked about polysaccharides, it's starch, and that would be like thousands of glucose units long. We're not talking thousands here with polyunsaturated fats. All this means is you have 2 or more. And usually it's only, maybe it's 2 or 3, honestly. 2 or more double bonds. So it's a little bit of a misnomer. It's not many. It's 2 or 3. Now notice, again, when we have double bonds, they can either be cis, right? The hydrogens on the same side, they're cis, or they can be trans. Now notice what happens to the shape of the molecule when it's cis. Okay, most fatty acids, right? I said they're typically even numbered, and they're also cis double bonds. They contain cis double bonds, which puts a kink in the molecule. If it's trans, right here the 2 hydrogens are on opposite sides. If it's trans, the molecule pretty much stays the same as if it were a saturated fat. Remember, the saturated fats lined up really well. Remember that in the previous slide? So here there's no double bonds. We can have another one here. And they line up really nice, and I said that increases the van der Waals interaction, and so they have higher melting points. Well, saturated fats kind of behave the same way. So first off, these saturated fats are not typically found in nature, so they're not typically, I just say found in nature or found in organisms. So they're artificial. We'll talk more about that in a little bit. They do exist, but they're artificial. You've probably heard about this before. If you look at food labels and whatnot, they'll talk about how much fat there is and how much trans fat there is versus how much total fat versus how much saturated or polyunsaturated. So what they're really talking about here are the double bonds. And when they're talking trans fat, they're talking about how these hydrogens are on opposite sides, and it ends up being a straight or linear molecule when it's a naturally occurring cis double bond. It puts this bend or kink in the molecule. And here we have oleic acid. This, I don't know if this is corn oil or whatever, but I'll just say it's vegetable oil. Okay, it's clearly a liquid, and that's because of this double bond that's here. The melting point, right, is below room temperature. It's below 20 degrees. So if you are in a room at 20 degrees, this is that temperature is above its melting point, and this will be a liquid. So as I mentioned before, unsaturated fats typically cis double bonds, and that puts these kinks in the molecule, and they have lower melting points, so they are liquids at room temperature. Hadn't talked about this yet, but lipids that are liquids at room temperature are referred to as oils. Okay, lipids that are solids at room temperature, so their melting point is above room temperature, so they have higher melting points. Lipids that are solids, these are referred to as fats. So fats and oils are both lipids. They both contain these fatty acids. It's just a matter of their melting point, and that also has to do with whether they contain double bonds like these unsaturated ones, or if they're saturated fat. So we'll put here unsaturated. Maybe I should put here cis unsaturated. And then the fats, these are going to be saturated. So we talk about saturated fats. We don't talk about saturated oils, saturated fats. So the way I like to think about this, and for whatever reason these molecules here with these kinks in them. They remind me of kinky oils, right? Because they are liquids at room temperature. Okay, so here we have some examples of monounsaturated and polyunsaturated. Remember I said there's usually just 2 or 3. This one actually has 4, but arachidonic acid is kind of special. We'll talk about him in a little bit. So you remember the saturated fats, stearic acid, for example, was also 18 carbons long, but its melting point was like 60 degrees or something, 60 degrees Celsius. Here, this is only 13. So you put a double bond in here and it really drops the melting point. And that's because they didn't put the kink in the molecule here, but these are cis double bonds. Okay, these are all cis. So there's little, also linoleic, linolenic. One thing I'll point out here is, if you remember, let me just number, this would be carbon number 1, carbon number 2, 3, 4, 5. This is 18 carbons long, 17, 18, right? Linolenic acid is also 18 carbons long. Okay, I'm not going to number it this way. Instead, I'm going to use these letters. Remember, we had alpha, beta. So we could either have an alpha hydroxy acid or a beta hydroxy acid, or in the next chapter we'll talk about alpha amino acids, where there's an amino group on this carbon, which is carbon number 2. So alpha, so the alpha carbon equals carbon 2. Carbon 3 is beta. The beta carbon equals carbon 3. And you just go through the Greek alphabet, but you really only need to know alpha and beta. And one other letter. The last letter of the Greek alphabet is omega. This is omega. Okay. So instead of identifying where these double bonds are from the front here, we're going to number or identify it from the back. So this is omega carbon, omega 1, omega 2, omega 3. So this is omega 3. There's a double bond. 4, 5, 6. This is omega 6. Right? Omega 3, omega 6. You may have heard of omega 3 and omega 6 fatty acids. These are found in fish oils. We'll talk a little bit more about them later, but they're supposed to be good for you. Compounds or fatty acids that have double bonds at omega 3 or omega 6 position. Again, arachidonic acid, this guy is going to be important later. It's C20, and it is used to form or make these prostaglandins. Again, real quickly, lauric acid, myristic acid, palmitic acid, these are all saturated, and they have high melting points. They are solids, and we refer to these as fats. There's an interesting one here, coconut oil. I just underline him, coconut and palm oil. Right, so coconut and palm oil, kind of interesting. These tropical oils we'll talk about in a little bit. But then we have the unsaturated. Right? Palmitic acid, 16. Palmitoleic acid, right? We have one double bond, and it goes from 62 degrees down to 0. Stearic acid, 69. You put one double bond here, you get oleic acid. It goes down to 13. So a huge difference there in the melting points just by putting those kinks in the molecule. Again, these are cis double bonds. Real quick learning check. You might want to pause the video here and test yourself. Okay, so go ahead and do that. So we have melting points, negative 17, 13, 69. Stearic acid is 18 carbons, and it's saturated. So saturated, it's going to have the highest melting point, so 69 degrees. Oleic acid is again 18. They're not isomers. I should point that out. Right? These are not isomers. All right, so real quick, if you have something like ethane, CH3, CH3, chemical form of C2H6, if you put a double bond in here and you get ethene, right, it is no longer C2H6, it's C2H4. So every time you put a double bond in, you lose 2 hydrogens. So again, not isomers. But they're pretty close in molecular weight just because of the number of carbons is the same. Right? So each one is about the same length. So one double bond, well, it's not going to be the lowest, like 2 double bonds. So this guy is going to be 13 degrees, and the lowest one, linoleic, with 2 double bonds, negative 17 degrees Celsius. Okay, as I mentioned before, prostaglandins. Right, these prostaglandins, they have 20 carbons. They are derived from arachidonic acid. Arachidonic acid. Now the name is, again, a misnomer. So prostaglandins were originally isolated from the prostate. Originally isolated from the prostate gland. So it was thought that, well, glands, what do? They secrete hormones and whatnot, like your thymus gland or your pituitary gland or your adrenal glands and so forth. However, it turns out that prostaglandins, these guys here, PGF1, PGF2, PGE1, these are the names. And again, you don't have to worry about the names or the structures. All you need to know is that they're prostaglandins, and I'll show you how you'll know that easily enough. They're derived from arachidonic acid, and they have 20 carbons. Okay. Now, prostaglandins do have hormone-like activity, but they are not hormones. The reason being is they are not produced specifically from one gland. There's other reasons too, but this is one of the main reasons. Prostaglandins are named that way just because they happen to be first identified from prostate tissue. It turns out that most cells actually make prostaglandins. So most cells make or produce prostaglandins. So they are not hormones. Not hormones. But they do have kind of quasi-hormone activity. We'll see in the next slide. All right, so prostaglandins can be produced from injured tissue, and it doesn't have to be prostate tissue. They're involved in pain, fever, the inflammation response. They're also involved in labor and delivery. They are not produced when anti-inflammatory drugs such as aspirin inhibit their synthesis. So there is an enzyme, I'm going to abbreviate COX. There's actually two. There's COX-1 and COX-2. This stands for cyclooxygenase. Cyclooxygenase. And there's several steps. That only shows one here, but there's several steps that take arachidonic acid to these prostaglandins. Aspirin blocks these enzymes. Okay, these are enzymes. We'll learn about enzymes in a little bit. We have a couple more weeks. But anyway, the aspirin that you made in the lab, right? Hopefully we're going to talk about this, but because of COVID, we're not going to mess around with it too much. But these analgesics like aspirin block the action, so they are inhibitors of these enzymes. So analgesics, right, inhibit COX-1 and COX-2. Is cyclooxygenase. So this is what I wanted to tell you. You don't have to know the structure of these prostaglandins or arachidonic acid. Remember, the other fatty acids were either maybe just straight across, right? Because they were saturated, or maybe they had a kink in the molecule, right, because they were cis double bonded and they had a unsaturation. Arachidonic acid is the only one that, because of these double bonds here, actually wraps around itself, so it forms this kind of loop. Okay, cyclooxygenase, well, makes a cycle and it oxygenizes it. So we've got this ring here, right? This 5-membered ring. So all you need to do is recognize this form of a prostaglandin. I'm not going to, try to trick you and put an alcohol group somewhere different. If you see, it's an acid, right? It's got, if you wanted to, you can go through and count all these carbons. There's 20 carbons. It has a cyclopentane ring, and it kind of wraps back on itself. Okay, so just recognize the general structure. Okay, and if you can do that, then you'll be fine. All right, as I mentioned before, omega-6 and omega-3 fatty acids, the vegetable oils are mostly omega-6. Right? Fish oils have omega-3. So again, here's carbon 1, carbon 2, carbon 3 double bond. Right? Carbon 1, 2, 3, 4, 2, 3, 4, 5, 6. Right? So this last carbon here is the omega carbon, and they're found in fish. Looks like rainbow trout here. And these omega-3 and omega-6 fatty acids are supposed to be good, healthy for you. So a couple of them that maybe you've heard about and it wouldn't be a bad idea to know them. We have icosapentaenoic acid, EPA. I'm not going to try to pronounce this one. Docosahexaenoic acid, DHA, just EPA, DHA. These are the ones that are supposed to be healthy for you, right? See, these are healthy. Good to have in your diet. So these omega-6, omega-3 fatty acids, DHA, EPA, they're cardioprotective, so they're good for your heart. So I call them heart healthy. Anti-inflammatory. This actually has to do with there are certain inflammatory diseases. Diseases such as rheumatoid arthritis, I'll just write RA, or autoimmune diseases. Inflammatory. Oh, sorry. So these are good. These are good to have in your diet, or if you take supplements for anti-inflammatory. Also for fetal development. So it's important for pregnant mothers, right? To have these in their diet. And lastly, they've been also known to help people with neurological problems, people with mild, I should say mild, or early signs of Alzheimer's, and also people with attention deficit disorder. There's a publication here, and you can find lots of information and studies online about the health effects and the usefulness of these omega-3 and omega-6 fatty acids.